We type in the following second order differential equation. D to x by dt squared plus 2 dx by dt plus 5x equals sine 3t times e to the minus t, comma, initial conditions, x of naught equals 1, comma, x dash of naught equals 1, comma, UC. UC meaning undetermined coefficients. We are ready now to solve this differential equation. Tap here for an answer. The black light goes on, it's calculating. When the light's gone, the calculation is done. The light is gone, so the calculation is done. Let's go down. There's your answer here at the bottom. We go now to the top and we explain. Starting with the homogeneous equation, where the right side is naught, we solve the following quadratic. Lambda squared plus 2 lambda plus 5 equals naught. Where do we get this quadratic from? The second order dE. You can see it's got the same form. Lambda squared is like your second derivative. Lambda is like your first derivative. So we solve it and we find that the roots are complex. Let's call it lambda 1 is minus 1 plus 2i. Lambda 2 is minus 1 minus 2i. The roots are in complex conjugates. Omega naught is the absolute value of your imaginary part. Yeah, it is 2. The general solution of the homogeneous equation is xh is capital A cos 2t plus capital B sin 2t times e to the minus t. 2 is omega naught. The minus 1 in front of the t here is the real part of our roots. Now for non-homogeneous equation, where the right side is sine 3t e to the minus t, we compare this particular problem of ours with this general form here. And let us compare the parameters that we see here with what we have here in our equation. The a here, which is the coefficient of the second derivative, is 1 in our case. The b, the coefficient of the first derivative, is 2 in our case. The c, the coefficient of x, is 5 in our case. The l, the coefficient in front, is 1 in our case. The omega here is 3 in our case. The k is minus 1, the coefficient of t here. Do not confuse this omega, which is 3, with this omega naught, which is 2. These parameters a, b, c, l, omega, k, we will refer to them below. And here we have our trial solution. Our trial solution is m cos omega t plus n sine omega t e to the kt. Have a look here. The k that we see here is the same k here, which in our case is minus 1. The omega here is the same omega here, which in our case is 3. The unknowns here, which really will be the undetermined coefficients here, will be m and n, and we must determine them. So then once we have determined them, then we have our particular solution. Now we can calculate m and n directly by these formulas here. M and n are given as the ratio of two determinants. Have a look at the bottom determinants. For m and n, they are the same. The top determinants nearly look like the bottom, except when we calculate m here, the first column that you see here is replaced here with 0 and L. When we calculate n, the second column that you see here is replaced with 0 and L. So we can determine m and n directly, and they are our undetermined coefficients. We determine them to be 0 for m and minus 1/5 for n. So our particular solution therefore is m cos omega t plus n sine omega t e to the minus t. So it will be 0 cos 3t minus 1/5 sine 3t e to the minus t. Now before we go on, let us just pause here for a moment when we look at m and n. Have a look here at the bottom determinants. Here we have ak squared plus bk plus c. That is the same quadratic that we see over here. A second derivative plus b first derivative plus c x. Right? But it's given in terms of k. So if k is not a root of this quadratic, and in fact it is this quadratic that we're talking about here, where the roots are complex. So k, which is minus 1, is not a root of this quadratic. So if k is not a root of the quadratic, then that quadratic won't be equal to 0. Right? So we have the full form as we see here, how to determine m and n. But what happens if k is a root of the quadratic? That means that ak squared plus bk plus c will be 0. So we will get a simplification when we determine m and n. In that case, when k is a root, that means that these quadratics that you see here, they will all be 0. Right? So we see simplifications here when k is a root. A further simplification is when k is a root, but it is also a double root. So that means for a root means the ak squared plus bk plus c will be 0. And for a double root means 2ak plus b will be 0 as well. How come? Because if you think about your formula for the quadratic, we have minus b over 2a plus or minus the square root of b squared minus 4ac over 2a for the roots. So if we have a double root, that means what's inside that square root, which is called the discriminant, which is b squared minus 4ac, that will be 0. So that means the root will only be minus b over 2a. That means k is equal to minus b over 2a. So if k is equal to minus b over 2a, twice of course, then 2ak plus b will be 0. So we get a further simplification. So if this quadratic is 0 and 2ak plus b is also 0, then we have quite some simplification here to determine m and n. That means we will have minus omega a squared, minus a omega squared there, minus a omega squared here. We have 0 here, 0 here. The same applies there. Right? And here will be 0. Here will be minus a omega squared. Here will be minus a omega squared. That will be 0. So we have quite some simplifications in the case of a root and in the case of a double root to determine m and n. But as it is given here, It is given for the case where k is not a root of the quadratic. Okay, so we have determined therefore our particular solution here, which is that. So the complete solution is homogeneous plus particular, which is a cos 2t plus b sin 2t e to the minus t plus 0 cos 3t minus 1 over 5 sin 3t e to the negative t. Simplification gives us this as your answer. But we have initial conditions. That means we can determine our A and B. X of naught, yeah, is 1. How do we get x of naught here? By substituting t equal to 0 in here. If you do that, you will just find A. So A is equal to 1 here for the first equation. The second equation, we have x dash is equal to 1. Now what is x dash? It's just the derivative of this, of your x. So that means you will have to differentiate that and put t equal to 0 in here. And if you do that, you get minus a plus 2b minus 3 over 5. So here we have two equations in two unknowns. We solve for capital A and B, and we find capital A is 1, capital B is 13 over 10. So we are ready now to write down our solution. Right? There are no unknown constants anymore. We have a solution. Right? We can even plot this, which we'll do in a moment. So here we have a solution, and here it is just given in another form. Now, how does this solution look? We can plot this. Right, let's go to the top. If we want to plot it, we will have to clear the screen first of all. So what we are going to do now, this answer that we see at the bottom, we are going to put inside the memory. All right, and how do we do that? Just a matter of saying that is input memory. So there we go. Right, that is inside the memory. We have a visible memory, by the way. So there's your answer. It's inside the memory. So we can now clear the screen. We won't quit. If we quit, then everything will be erased, including what's inside the memory. So it's just a matter of clearing the screen. Yeah. Okay, we are ready to do that. Yeah. So we are ready now to plot this. Okay, let's go to graphics. To the graph, let's say t going from north to 5. Yeah. And now just a matter of going inside here, and now we say recall memory. Okay. So we can plot this. Let's type here for an answer. There it is. There's your graph. That is what your solution look like. And just before we leave, we just mentioned here that there are also other methods that we can use to solve second order differential equations. They are, for instance, the plus transforms. They are variation of parameters. They are D operators. They are, for instance, the plus combining it with the convolution integral, and so on. But those methods we will discuss in future.